Hey guys, I'm William and welcome back to the channel. In this video, I'll be going over the solutions to the October edition of the California Math League. Please note that you can pause the video to look at each problem before I go over the solutions, or alternatively, use the link posted in the description to glance at them. Shall we get started? Alright, problem 1. What's the least possible length of one side of a square whose perimeter is the square of a positive integer? It's known from basic geometry that the perimeter of a square is 4 times the side length of that square. But we can minimize the perimeter if we also minimize the side length. Let's just find the side length. There's only one other condition, that the perimeter has to equal the square of a positive integer. That's it. Therefore, we can just simply focus on that condition. We know that the smallest number to equal the square of a positive integer is 1, as is equal to 1 squared. That's the perimeter we're seeking for. Now we have to divide by 4 to find the side length, and we'll get 1/4. The simple strategy is all we have to do read the problem and use some basic knowledge. Moving on to problem 2, what's the only order quadruple of integers a, b, c, and d for which a plus 2b plus 3c plus 4d equals 30 and a squared plus b squared plus c squared plus d squared equals 30? I feel like this problem has multiple solutions, so I'll give each here. The given expressions are equal to the same number in 30. They're kind of similar, so why not experiment with them? In other words, we can equate the addends of each expression with each other and obtain the variables. What I did was set a equals a squared, 2b equals b squared, 3c equals c squared, and 40 equals d squared. And that gave me a equals 1, b equals 2, c equals 3, and d equals 4. We can verify that the solution works. The official solution from the official packet did this. So we multiplied the first equation by 2, and then we have to subtract that from the second equation. And once we do this, we have an equation in which we can complete the square for each of the variables to arrive at a sum of squares of expressions that have to equal 0. But note that each expression is integral, and therefore they're real. Their squares have to be non-negative, so each of them has to equal 0. Since each square is 0, a minus 1 equals 0, b minus 2 equals 0, and so on. We can get the solution like before, but I want to introduce you to a final solution, and that's going to be really cool. When I first saw this problem, I was thinking Cauchy-Schwarz. It's one of the advanced algebraic inequalities, and you can look up and to see what it is, and you can see the proof, but specifically for 4 terms, a squared plus b squared plus c squared plus d squared times x squared plus y squared plus z squared plus w squared has to be greater than or equal to ax plus by plus cz plus dw squared. And that holds if all the variables are real numbers. Equality holds if and only if there's a constant t, such that at equals x, bt equals y, ct equals z, dt equals w, or vice versa. That means that the sequence a, b, c, and d, and x, y, z, and w, they have to be what I call proportional. So there's a constant. When you multiply one of those sequences by, you get the other sequence. So what I did was set x equals 1, y equals 2, z equals 3, and w equals 4. And notice that when we plug into these expressions and use the given equations, the expressions of the inequality are equal. As a result, there has to be a constant t where a equals t, b equals 2t, c equals 3t, and d equals 4t. We can use the first equation to obtain t equals 1 and the solution. As for the strategies, I say we have to use the givens in a crafty way, manipulate the equations most advantageously to solve for the variables. Or we can guess and get really lucky here. Next is problem 3. What's the least positive integer n for which the sum of the digits of both n and n plus 1 are even integers? Since n has to be a positive integer, and this is a CAML problem, I feel like we can go a bit easy. We should definitely start counting from 1. But notice that if n is from 1 to 8, the sum of the digits of n and n plus 1, it's going to be themselves. What I mean is that, for example, if you're calculating the sum of the digits of 7, we just get 7, right? But note that n and n plus 1 will always have different parity. For example, if 6 is even, 7 can't be even, it's odd, right? But that means that if n is from 1 to 8, it can't work. We're looking for even integers for both the sum of the digits of the two numbers. But consecutive numbers cannot both be even. One has to be odd and one has to be even. If n equals 9, the sum of the digits of n is simply 9, which is not even. How about from 10 to 18? Unfortunately, there's no cigar. Why? Well, it's due to the fact that when you calculate the sum of the digits of the integer 1n, where n is a digit from 0 to 8, it's going to equal 1 plus n. But we know that we're going to deal with consecutive numbers again. And we have the form 1n. And so the sum of the digits of the integers 1n and 1n plus 1, they're going to be consecutive. And as we said before, consecutive numbers cannot both be even. But when we look at n equals 19, that's the first number that works through a problem and why the solution is 19. To get the idea on the approach, start small, is we have to look for the minimum of something. I would experiment until the solution is found. We can use other conditions, knowledge, or logical principles to help our work. But we have to make sure in minimum problems, we have to make sure it works, but the smaller values don't, which solves the problem. Scrolling to problem 4, of the positive integers less than 1 million that are also cubes in integers, how many are multiples of 10? This is very tricky, so how to go with it? We can verify that the only way for the cube of an integer to be even is for the original integer to be even. But it may be hard to observe that if a cube is divisible by 5, then the original number has to be divisible by 5. This is something called number theory. And I may have to use knowledge that may be hard to prove. But let's think about this. We know that n cubed is n times n times n. There's a theorem that says that if a product of numbers, or I should say integers, is divisible by a prime p, then one of the multiplicand has to be divisible by p itself. That means that either n or n or n has to be divisible by 5. So either way, n has to be divisible by 5. So there we go. If a number is divisible by 10, it has to be divisible by both 2 and 5. So the cube of an integer is divisible by 10 if and only if the original integer is divisible by 10 itself. There are 99 integers such that their cubes are positive integers less than a million. So these numbers, they're exactly the first 99 positive integers. The numbers we're seeking for in this range are the numbers divisible by 10. So we can go 10, 20, all the way to 90. And so there are 9 numbers in my count. So the solution is 9. So how did we go about this way? Casework. Think about what numbers will work. But at the end, it's a number theory problem. So if you're really confused, I recommend you look up number theory resources online, and you can gain a whole bunch of knowledge that may help you do the competitions better. So here's problem 5. As seen in the diagram not drawn to scale, a rectangle and a circle intersect so that adjacent segments on one side of the rectangle have length 4 and 6, while on the opposite side, one segment has length 3. How long is the chord of the circle that's labeled with a question mark? When I first saw this problem, I knew that solving geometry problems like this requires me to draw additional lines to arrive at the solution. In fact, this tactic of adding new lines is exactly what we'll be using here, and that's a method that can be used to solve most geometry problems. I labeled the points here, then I drew the radius lines and the vertical lines passing through O. That way, I can make right angles, demonstrate congruences, and use the right congruence theorems and shape properties to solve for what I need. You can in this video, what you can see on the screen is me drawing lanes and using congruence theorems to go prove that the question mark that we're looking for is 8. Finally, there's problem 6. When I wrote each of the first n positive integers on a different card, I split these cards into 3 piles, which may or may not contain different numbers of cards. For how many distinct values of n less than 2022 can the numbers written on the card in each pile have the same sum? It's definitely the hardest question in the contest so far. Even harder than question 2 probably. Maybe we can start small. It may be easy to find that n equals 5 is the smallest n that works for the final question. We can consider the piles 1, 4, then 2, 3, then 5. But how are we going to check the other values of n? Because n is 2022, that's really large. But just know that we have to split the cards into 3 piles such that each pile has the same sum as the others. We don't know what the common sum is, but it has to be an integer. You multiply that common sum by 3, we have to have the sum of all the cards divisible by 3. But what's the sum of the cards? We have to recall that that's each of the first n positive integers. It doesn't matter what order you add these integers. It has to be 1 plus 2 plus 3 plus all the way to n. And that's equal to n times n plus 1 divided by 2. That's the famous Gaussian sum right there. But what n makes this sum divisible by 3? By small inspection, all n except for 1, 4, 7, 10, work. But why do integers of the form 3k plus 1 fail and the others work? Know that for n equals 3k, we have the sum equals 3k times 3k plus 1 slash 2. And for 3k plus 2, if that is equal to n, then we have 3 times k plus 1 times 3k plus 2 divided by 2. Both resulting numbers have 3 as a factor, and the denominator can't cancel that 3 out. But when we test 3k plus 1, we get 9 times k squared plus k plus 2 divided by 2. Just know that if this number is divisible by 3, then the numerator has to be divisible by 3 as well, but that's a number of the form 3n plus 2, so they can't work. We just reached the stage of determining what n could possibly work, but do these valid n's actually work? Recall that n equals 5 was the smallest n that satisfied the problems. N equals 6 turns out to be valid as we can split the cards into 1, 6, 2, 5, 3, 4. For n equals 8, that's 1, 3, 8, 2, 4, 6, and 5, 7. N equals 9, we have 1, 5, 9, 2, 6, 7, and 3, 4, 8. Here's how to show the validity for bigger n. This is called induction. I'm going to claim that if n works, n plus 6 works as well. The numbers in the n plus 6 deck that aren't present in the n deck are n plus 1, n plus 2, and on our way to n plus 6. We compare the remaining cards as n plus 1 with n plus 6, n plus 2 with n plus 5, and n plus 3 with n plus 4. Each has a common sum of 2n plus 7. Let's consider the piles we formed from the n deck. We can add the small piles that we just formed, each small one, into the big ones from the n deck, and since we have the same sum from the n deck, from the piles, and then we add 3 small piles that also have a common sum, we're going to have bigger piles which should share the same sum. Add these pairs to the piles, and we prove the claim. We proved that 5, 6, 8, and 9 work. So therefore, 11, 12, 14, 15, 17, 18, 20, 21, it should also be good. But to solve the real question, we're looking for the number of n less than or equal to 2022 that work. But 2022 is 3 times 674. And there's a fact that since 2022 is divisible by 3, there are exactly 674 numbers, each of the 3k, 3k plus 1, and 3k plus 2 types. But don't forget, we have to exclude the 3k plus 1 because such n can't possibly work. So we can bring down the total by 674. But don't forget that 2 and 3 both fail. So the official count and solution is 1346. And for the strategies, we need to have fun with small cases. We need to analyze the problem very carefully to find additional conditions for the problem to hold true. In this case, it was the total sum of all cards that played the key role into solving Q6. We have to make some useful conclusions about what's given in the problem, narrow the question down further until it's in a solvable state. We have to make sure that all our solutions work. This is a construction problem, and we have to use our time and construct a configuration that works. If we want to prove a pattern, we can definitely use induction. But anyways, that's the end of the video. I really hope that it helped you guys go through the solutions of the problems of the October 2022 CAML math contest. If you knew how to solve all the problems, that's great. But otherwise, I'm so glad that you can use this to improve your skills. Thank you for listening, and I'll see you next time.